Welcome to the third lab of electronic laboratories. This time we'll experiment on Thevenin and Norton equivalent circuit. Before I get into the details of the experiments, I'd like to remind everyone of several important notes. In this experiment, the function generator output load setup should be set to high Z. And set your oscilloscope probe to 1x. Think and estimate before you use your multimeter. Use a proper measurement mode and range will get you better results and protect your device. We have 5 experiments in this lab. Experiment 1. In this lab, we're going to verify the concept of equivalent circuit. This is the original circuit, and this is the Thevenin equivalent circuit of the original circuit, and this is the Norton equivalent circuit of the original circuit. Of course, these two circuits are also equivalent. You may calculate the resistance, voltage, and current to verify. Here you can see that there is a current source. How do we implement a current source? Use the current limit function in the power supply. Set the current limit to desired value. In this case, for instance, 10 milliampere. Then turn the voltage higher than the value required to generate the current. This will make the power supply output the desired current steadily. However, in this case, because the current 10 milliampere is very small, the number on the power supply may not be accurate. Use your multimeter to measure the current and adjust accordingly. If you find it very hard to achieve the goal, you may use the BK precision power supply. The machine has better precision than the original one, so it should be easier to adjust. Please review how to set the current limit. Experiment 2. First, you have to construct this circuit, but there is some resistor value that you do not have. For example, this 33 kilo ohm resistor. Take a variable resistor of 50k ohm and adjust it to the desired value. Use your multimeter to ensure that you have the desired resistor value. After you completed the circuit, measure the V out and I out with different resistor. Then repeat the measurement on your Thevenin equivalent circuit. This experiment will make you understand the Thevenin open circuit voltage. Experiment 3 wants you to observe the phenomenon of frequency response and the behavior of capacitor when charging and discharging. In the first part, we will give the circuit a sine wave input. We can see the V out changes with different frequency. This is called the frequency response. We hope that you refer to your textbooks and understand the meaning behind this phenomenon. In the second part, we will use the square wave to observe the charging and discharging behavior. Recall that the square wave has a high level and a low level. We charge the capacitor during the high level part of the wave and discharge it during the low level part. This requires us to give the capacitor enough time to charge and discharge. A 1 kHz square wave will provide 500 milliseconds for both charge and discharge. Evaluate the time constant from the observed curve and its equivalent resistance. Then repeat the lab with a Thevenin equivalent circuit and compare the results. During this lab, you should record the frequency clearly. Make sure that you have the frequency on your photo. When you want to calculate the time constant, you want to ensure that capacitor is fully charged or discharged. Remember that it takes time to do so. Therefore, for some high frequency input, you cannot evaluate the time constant. But how do you know if it is fully charged or discharged? We can see from the figure that when it's fully charged, the voltage will reach a flat level. The same for discharging. When you see this kind of figure, it may not be fully charged. To calculate the time constant, you will find on your textbook that when the voltage is 0.632 times the high level voltage, the time will be the time constant we're looking for. We will use this relation to find the time constant. Find the desired voltage and measure the time passed. This is exactly the RC time constant. Experiment 4. We will now verify the superposition theorem. We will measure 3 cases. One with this voltage source on and the other voltage source off. Then we'll measure this voltage source on and the other voltage source off. Finally, we'll measure with both voltage source on. We will then add both measurements with one voltage source and check it if it equals the measurement with 2 voltage source. This will verify the superposition theorem. Note that when we turn one voltage source off, short circuit the wires of its both ends. If you just turn the voltage source off, it will become open circuit, which is incorrect. Experiment 5. This is a simple experiment that wants you to compare the LT spice and our measurements. Use 12 resistors to construct the circuit and measure the circuit and compare with LT spice simulation result. That's all for this lab. See you next time.